Hello, friend. Welcome back to another quiet journey through the cosmos. I'm glad you're here. Some nights the world feels wider than it should. Stars breathe slower. Time folds in silence. Maybe that's just the mind listening to itself. But tonight we're going somewhere smaller. So small that the very idea of place begins to dissolve. We're drifting toward the edge of everything we can know. A boundary written not in stone, but in the fabric of reality itself, where space crumbles, where time stutters, where the universe whispers its final secret and falls silent. Before we begin, if you find comfort in these quiet journeys, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories told softly, and ring the little bell, not for noise, but so the next quiet night can find you again. Now, let's drift. It was December of 1899. Berlin lay cold and gray. In a modest study lit by gaslight, a German physicist named Max Planck sat hunched over sheets of paper, scribbling equations that refused to behave. He was 41 years old, methodical, conservative, not the kind of man who sought revolution. He was simply trying to solve a problem about light and heat. Something practical, something ordinary. But the numbers kept pulling him somewhere strange, somewhere he didn't want to go. Planck was studying blackbody radiation, the way hot objects glow. Imagine a piece of iron heated in a forge. First it glows red, then orange, then white hot. Classical physics said the glow should grow infinitely bright at short wavelengths, a prediction so absurd it was called the ultraviolet catastrophe. But nature didn't catastrophe. It glowed gently, predictably. Planck needed to know why. So he made a guess, a mathematical trick. He assumed that energy wasn't continuous like water flowing from a tap, but came in tiny indivisible packets, quanta, little grains of light. It worked. The equations fell into place. The catastrophe vanished. But Planck himself was uneasy. He called it an act of desperation. He didn't believe energy was really quantized. He thought it was just math, a tool, a convenience. But hidden inside his desperate trick was something far deeper. By combining three fundamental constants of nature, the speed of light, the gravitational constant, and a new number he'd just discovered, Planck's constant, he stumbled upon a set of natural units, the smallest possible length, the shortest possible time, the faintest tick of existence. He wrote them down almost as an afterthought. He had no idea what they meant. Scientists suggest he barely mentioned them in his original paper. Yet those numbers would outlive him. They would become the boundary of all physics, the Planck scale, Planck length, 1.6 times 10 to the negative 35 meters. Imagine shrinking a human hair by a factor of 1 billion, then shrink that again by 1 billion, then again. You're not even close. The Planck length is so incomprehensibly small that if you expanded a single atom to the size of the observable universe, the Planck length that would still be smaller than a human cell. It's the pixel of reality, the grain, the point where the smoothness we see, this continuous flow of space, begins to fracture into something else, something unknown. Planck time, 5.4 times 10 to the negative 44 seconds. The time it takes light, the fastest thing in existence to cross one Planck length. If you could count every Planck time unit in a single second, you would need more numbers than there are atoms in all the stars of the Milky Way, multiplied by itself over and over until counting itself lost meaning. It's the shortest moment that can exist. Before it, the word before has no home. These aren't measurements we made. We've never observed a Planck length. We never will. They're not sizes we stumbled upon in a laboratory. They're prophecies written in the mathematical bones of the universe. Planck derived them purely from theory, from combining constants that govern light, gravity, and quantum mechanics. He found the edges of reality with nothing but ink and thought. And what he found was this: there is a smallest possible size, a shortest possible time. Not because our instruments fail, not because we lack imagination, but because below that scale, the concepts themselves, distance, duration, space-time, stop making sense. The universe has a resolution limit, like an old photograph dissolving into dots. If you zoom in too far, reality pixelates. At the Planck scale, the picture ends. Scientists often speak of the Planck scale with a kind of reverence. It's where Einstein's gravity and Heisenberg's quantum mechanics collide. Two titans of 20th century physics, both flawless in their own domains, both unable to coexist. General relativity tells us that space and time curve smoothly under the weight of matter. It's the realm of stars, galaxies, black holes. Continuous, elegant, predictable. Quantum mechanics tells us that at tiny scales, everything jitters and jumps. Particles blink in and out of existence. Energy fluctuates wildly. Nothing is smooth. Nothing is certain. And at the Planck scale, these two descriptions try to operate in the same place at the same time, and they tear each other apart. Imagine trying to measure the curvature of space at a scale smaller than the Planck length. Quantum mechanics says that at such tiny distances, energy fluctuations become so violent that they would curve space so intensely they'd create miniature black holes. Not holes you could fall into. Holes that exist for less than a Planck time and then vanish. Space itself would boil. It would froth like the surface of a stormy sea, bubbling with temporary tears in the fabric of reality. Some physicists call this quantum foam, a name that sounds soft, almost playful. But it describes the complete breakdown of everything we think we know about geometry. John Wheeler, the physicist who coined the term, once said that if you could see space-time at the Planck scale, it wouldn't look like a smooth stage where events unfold. It would look like a chaos of wormholes, black holes, and pathways twisting through dimensions we can't name. A foaming, seething ocean of geometry where cause and effect blur, where past and future tangle, where the notion of a single point in space loses all coherence. He imagined it. We still do. Because no experiment, no telescope, no particle accelerator will ever take us there. Why not? Because to probe the Planck scale, you'd need energy. Enormous energy. The kind of energy that doesn't just illuminate, it creates. To see structure at the Planck length, you'd need to concentrate so much energy into so small a space that you'd form a black hole. The very act of looking would destroy what you're trying to see. It's as if nature has placed a curtain at the edge of reality and said gently but firmly, no further. The Planck scale is not a wall, it's a whisper, a soft boundary where the rules we've built, space-time, matter, energy, begin to fade into something we have no words for. Some believe that at this scale, time isn't a river flowing forward, it's a mist. Space isn't a container, it's a suggestion. The universe in its deepest heart may not be made of things at all, but of relationships, possibilities, patterns without form. Max Planck died in 1947, nearly 50 years after his discovery. He lived through 2 world wars. He lost his son to the Nazi regime. He witnessed his equations birth the atomic age, a consequence he never intended. But the scale that bears his name outlasted every tragedy, every triumph. It remains untouched, a monument not to human ambition, but to human limitation. A reminder that some truths live beyond proof, beyond sight, beyond the edge of what we can hold. And yet, here we are, reaching toward it, not with instruments, not with certainty, but with wonder. Because even if we can never see the Planck scale, even if it remains forever hidden, it still shapes everything. The Big Bang began there. Black holes end there. The quantum and the cosmic, the smallest and the largest, they meet in that impossible place and dance in the dark. Perhaps that's the real gift, not the answer, but the question. What happens when we reach the edge of everything we can know? Do we stop? Or do we learn to be comfortable in the not knowing, to sit quietly at the boundary and listen? Tonight we've only just arrived. The Planck scale is a country of strange numbers and stranger ideas. In the moments ahead, we'll wander deeper. We'll meet the numbers themselves, those impossibly small figures that describe the finest grains of reality. We'll see how they were born, not from observation, but from the marriage of three fundamental forces. We'll explore what they mean and what they can't mean. We'll drift into places where language stumbles and imagination begins. But for now, just rest. Let the idea settle gently. There is a smallest size, a shortest time, a final edge. And it's written not in ink, but in the silent mathematics of everything. You don't need to understand it all, just feel it. The universe has boundaries, and they are more beautiful than we ever imagined. What comes next are the numbers themselves, the impossible, the infinitesimal, the almost holy. The Planck unit's the smallest words the universe has ever spoken. We'll write them down together, slowly, carefully, and see what they reveal. Numbers can be gentle things. 1, 2, 3. We count stars, count breaths, count moments. But some numbers refuse gentleness. They stretch beyond comfort, beyond imagination, into territories where even mathematics seems to whisper, I don't know what this means anymore. The Planck units are those numbers, not measured, not observed, but calculated pure and cold from the deepest laws we know. And when you write them down, when you see them staring back at you from the page, something inside you realizes the universe has a handwriting, and it's smaller than we ever dreamed. Let's begin with the Planck length, 1.616255 times 10 to the negative 35 meters. To understand how small this is, we need comparisons that break. If you took a single hydrogen atom, the simplest atom in existence, and expanded it to the size of the entire observable universe, 93 billion light years across the Planck length would still be about the size of an average tree on Earth. Not invisible, but lost. Impossibly lost. It's not just small, it's a different category of small. A smallness that makes electrons look like planets. Scientists suggest that the Planck length might represent the smallest meaningful distance in nature. Not the smallest we can measure, but the smallest that can exist. Below this scale, the very concept of distance may dissolve. Imagine trying to measure something smaller. You'd need a ruler made of light of energy, of something that could fit into the tiny space. But concentrating enough energy into such a small region would warp space-time so violently that it would collapse into a black hole. The act of measuring would erase the thing being measured. Nature has hidden herself behind a veil of her own design. Here's a way to feel it. Take a single grain of sand. Tiny. Right now, imagine dividing it into 1 billion pieces. Take one of those pieces and divide it again by 1 billion. Do that about 4 more times. You're approaching the scale of a proton, but the Planck length is still 10 to the 20th times smaller than that proton. 20 orders of magnitude. It's not a number we can picture. It's a number we can only write and then sit with quietly until the strangeness of it settles in. Then there's Planck time. 5.391247 times 10 to the negative 44 seconds. The shortest tick the universe knows. Imagine the fastest thing you can think of. A heartbeat, a blink, the flash of a camera. Light itself crosses about 300,000 kilometers in 1 second. In 1 Planck time, light travels 1 Planck length. That's it. The smallest journey possible. If you wanted to count how many Planck times fit into a single second, you'd need a number with 44 digits, more than the number of stars in the observable universe, more than the number of grains of sand on every beach on Earth. It's a duration so brief that calling it an instant feels generous. Some physicists wonder if time itself is made of Planck time units like frames in a film. Each moment a frozen picture, the universe advancing frame by frame, too fast for us to notice the jumps. Others suggest time might be continuous, smooth all the way down, and Planck time is simply the limit of when our descriptions fail. We don't know. Both possibilities feel equally strange. Either time is stitched together from invisible threads or it flows forever, even where meaning ends. Now, the Planck mass. This one surprises people, because while Planck length and Planck time are incomprehensibly small, Planck mass is almost ordinary. 2.176434 times 10 to the -8 kilograms, about 22 micrograms. The weight of a single grain of sand, a flea's egg, a speck of dust dancing in sunlight. You could hold it. You could lose it in the folds of your sleeve. Yet this tiny mass concentrated into a volume the size of the Planck length would contain so much energy that it would immediately become a black hole. A microscopic singularity existing for less than a Planck time before evaporating in a burst of radiation. The Planck mass is the threshold where matter stops behaving like matter and becomes pure gravitational collapse. It's strange to think that something so light could be so extreme. We imagine black holes as vast, hungry giants in space swallowing stars. But at the Planck scale, a black hole can be smaller than an atom and weigh less than a snowflake. It's a reminder that gravity doesn't care about size. It cares about density. Squeeze enough mass into a small enough space and the universe folds in on itself, no matter how little you started with. Then comes Planck temperature, 1.41678 4 times 10 to the 32 Kelvin. A number so hot it scorches the imagination. For reference, the core of the sun burns at about 15 million Kelvin, the hottest thing we've ever created in a laboratory inside particle colliders reached around 5 trillion Kelvin for a fraction of a second. The Planck temperature is 100 million trillion times hotter than that. At this temperature, particles don't just move fast, they cease to be particles. Energy and matter blur into a single indistinguishable plasma. Space-time itself writhes. Some researchers believe the universe itself reached Planck temperature during the first moments after the Big Bang, in that unimaginable instant before even atoms could form. Here's what makes Planck temperature particularly haunting. It might be the highest temperature that has any physical meaning. Beyond it, the concept of hot loses its grip. Thermal energy would be so concentrated that it would create black holes out of pure heat. The universe would not allow anything hotter to exist, not because we can't make it, but because reality itself forbids it. It's a ceiling written into the laws of thermodynamics and gravity, a final rule that even the Big Bang could not break. And here's the beautiful part. Max Planck didn't derive these numbers by experiment. He never heated anything to Planck temperature. He never measured a Planck length. He found them purely through mathematics. By combining 3 constants, the speed of light, which governs how fast information can travel, Newton's gravitational constant, which governs how mass warps space, and Planck's constant, which governs the quantum graininess of energy, he created natural units. Units that don't depend on human definitions like meters or seconds. They're written into the structure of the cosmos itself. If aliens exist on the far side of the universe and they understand physics, they would discover the exact same Planck units. Not because we taught them, but because the universe did. It's worth pausing on that. These numbers are universal. They don't change if you use different measuring sticks. They don't shift with perspective. They're the same in every galaxy, every dimension, every moment since the Big Bang. In a sense, the Planck units are the universe's way of saying, this is my true scale. This is the grammar I'm written in. Let's try another comparison one that might make the smallness more visceral. If you took the period at the end of this sentence and zoomed in, you'd see molecules then, atoms then, protons and neutrons. Keep zooming. Inside the protons, you'd find quarks bound together by gluons vibrating in a quantum haze. But even quarks, the smallest particles we know, are still trillions of times larger than the Planck length. To reach the Planck scale from a quark, you'd have to shrink by a factor larger than the ratio between a human and the entire Milky Way galaxy. It's not just small, it's a smallness that breaks intuition. And yet some theories suggest that at the Planck scale, space might not be empty at all. It might be woven stitched together from loops of quantum gravity, or vibrating with strings of energy, or bubbling with virtual particles that blink in and out of existence faster than time itself can record. We call these ideas string theory, loop, quantum gravity, quantum foam. They're attempts to describe what might live in that impossible space, but they remain for now mathematical poetry, beautiful, unproven, whispered, not shouted. One of the most common mistakes people make when thinking about the Planck scale is assuming it's the size of the smallest particle. It's not. Electrons, quarks, even neutrinos, they're all vastly larger. The Planck length isn't the size of anything we've found. It's the size where our equations stop working, where the smooth fabric of space-time we rely on starts to fray, where quantum mechanics and general relativity, those two great pillars of modern physics, both throw up their hands and say, "We don't know what happens here." Think of it like this. Imagine you're drawing a picture with a pencil. You can draw fine lines, tiny details, intricate patterns. But there's a limit to how small you can draw, set by the width of the pencil's graphite. The Planck scale is the universe's pencil tip. The finest detail reality can sketch. Beyond that, the drawing smudges. The lines lose meaning. The picture becomes something else entirely, something we don't yet have the tools to see. So, why do these numbers matter if we can never reach them? Because they tell us where the mysteries live. Every unsolved problem in physics, the nature of black holes, the origin of the Big Bang, the unification of forces, they all point back to the Planck scale. It's the place where the story begins and ends, where the universe was born and where it might one day return. To understand the Planck units is to understand the limits of knowledge itself, not as a failure, but as a map. Here the map says, be humble. And perhaps that's the real lesson, not that we're small though we are, but that the universe has layers we'll never touch, depths we'll never sound. And that's okay. Wonder doesn't require certainty, it only requires attention. And these numbers, these impossibly small, impossibly extreme measures, they deserve our attention. Because they're not just numbers, they're the universe's signature. The smallest letters in the longest story ever told, we've written them down now. Planck length, Planck time, Planck mass, Planck temperature. 4 numbers pulled from the void by mathematics alone. But knowing the numbers is only the beginning. What do they mean? What happens when you actually try to operate at those scales? When gravity and quantum mechanics stop being polite and start colliding, that's where the real strangeness begins. That's where space-time itself begins to boil. There are places in physics where 2 worlds touch but cannot hold hands. One world is vast, smooth, predictable. The other is tiny, jittery, strange. For a century, they've coexisted by staying apart. General relativity governs the large, the heavy, the slow curve of space-time around stars and galaxies. Quantum mechanics governs the small, the light, the probability clouds of electrons and photons. Both theories work beautifully. Both have been tested thousands of times. Both have never failed, except when they meet. At the Planck scale, where the very large tries to describe the very small, these 2 giants collide. And the collision is not gentle. Albert Einstein published his theory of general relativity in 1915. It was a revolution wrapped in geometry. He showed that mass and energy don't pull on things through some invisible force. Instead, they bend the fabric of space-time itself. Planets orbit the sun not because they're tugged by gravity, but because they're rolling along curves in the space-time the sun has warped. It's elegant. It's visual. You can almost feel it. A heavy ball on a stretched rubber sheet and marbles rolling in spirals around it. The math is complex, but the idea is simple. Mass tells space-time how to curve. Space-time tells mass how to move. Then in the 1920s, quantum mechanics arrived. Heisenberg, Schrödinger, Bohr, Dirac. They discovered that at tiny scales, particles don't have definite positions or speeds until you measure them. They exist in clouds of probability. An electron isn't here or there. It's everywhere at once, smeared across space until the moment you look. And energy doesn't flow smoothly. It comes in chunks and quanta like water dripping from a faucet instead of pouring from a river. The universe at its smallest is grainy, uncertain, flickering. For decades, these two theories lived in peace because they operated in different kingdoms. Relativity described black holes, the bending of starlight, the expansion of the cosmos. Quantum mechanics described atoms' radioactive decay, the glow of heated metal. They never had to speak to each other, but at the Planck scale, the kingdoms overlap. You have objects so small that quantum mechanics must apply, but so dense that gravity cannot be ignored. And when you try to use both theories at once, the math explodes. Infinities appear. Predictions become nonsense. The equations so reliable in their separate domains shatter against each other like glass. Here's why. Quantum mechanics says that the smaller the space, the greater the uncertainty in energy. If you try to pin down a particle's position very precisely, its energy becomes wildly uncertain. At the Planck scale, this uncertainty is so extreme that virtual particles' tiny fluctuations of energy constantly blink in and out of existence. They're called vacuum fluctuations. The vacuum isn't empty. It seethes with temporary particles borrowing energy from nothing and paying it back before the universe notices. But general relativity says that energy curves space-time. So if the vacuum is fluctuating with energy, space-time itself must be fluctuating. At the Planck scale, these fluctuations become so violent that space-time stops being a smooth fabric. It becomes turbulent, chaotic. Some physicists describe it as a foam, a froth of quantum bubbles, where the geometry of space twists tears and reconnects faster than time can measure. Imagine the surface of the ocean during a storm, but the waves are dimensions themselves, rising and falling, colliding and breaking apart. That's the quantum foam. It's not something we can see. It's not even something we can properly imagine. But the math suggests it's there roiling beneath the surface of reality. John Archibald Wheeler was the physicist who named it. In the 1950s, he spent years trying to reconcile quantum mechanics with gravity. He was Einstein's colleague, a brilliant mind who also gave us the term black hole. Wheeler believed that at the smallest scales, space-time wouldn't just fluctuate. It would become a labyrinth of wormholes, tiny tunnels connecting distant points, opening and closing trillions of times per second. He called it space-time foam. And though he could never prove it existed, the idea captured something essential. At the Planck scale, geometry itself is uncertain. Let's make this concrete. Imagine you're trying to measure the shape of space-time at a scale just slightly smaller than the Planck length. According to Heisenberg's uncertainty principle, the energy required to probe that scale would be enormous. So enormous that it would create a gravitational field strong enough to warp the very space you're trying to measure. You'd be changing the thing you're observing by the act of observing it, not in a small way, in a catastrophic way. The measurement itself would rip a hole in space-time. A microscopic black hole would exist for an impossibly brief moment and then evaporate in a flash of radiation. You can't measure the Planck scale because measurement at that level is destruction. This is the heart of the problem. General relativity assumes space-time is smooth, a continuous stage on which events unfold. Quantum mechanics assumes you can always measure things more precisely by adding more energy. But at the Planck scale, adding more energy doesn't give you more information. It creates black holes. The two theories don't just disagree. They contradict each other at the most fundamental level. One says space is a calm surface. The other says it's a boiling sea. And both can't be right in the same place at the same time. Think about what this means. Every object, every particle, every ripple of light exists within space-time. Space-time is the container, the canvas, the foundation. But at the Planck scale, the foundation crumbles. the canvas tears, the container leaks. It's as if reality itself has a threshold below which the concept of location dissolves. You can't ask where something is if space itself is uncertain. You can't ask when something happened if time is foaming. This isn't a failure of human knowledge. It's not that we haven't built good enough instruments or discovered the right equation. It's that the question itself might not make sense. Asking what happens below the Planck scale might be like asking what's north of the North Pole. The question assumes a framework, a geography that doesn't exist. Some physicists believe that space and time might not be fundamental at all. They might be emergent like temperature or pressure properties that only appear when you zoom out from something deeper. But what that deeper thing is, we don't know. We only know its shadow. Let me give you an analogy. Imagine you're looking at a photograph. From a distance, it's smooth. You see a face, a landscape, a sunset. But if you zoom in close enough, you start to see pixels, little squares of color. Zoom in further, and the image becomes meaningless. It's just dots. No face, no landscape, just information encoded in a grid. The Planck scale might be reality's pixel, the point where the smooth image of space-time breaks into something more fundamental. But unlike a photograph, we can't zoom out and then back in to check. We're stuck inside the image trying to understand the pixels from within. Now, here's where it gets eerie. Some researchers suggest that these quantum fluctuations, this foam, might have consequences we can almost detect. In the 1970s, Stephen Hawking showed that black holes aren't entirely black. They emit radiation now called Hawking radiation because of quantum effects near the event horizon. Virtual particles appear in pairs at the edge of a black hole. One falls in, the other escapes. To an outside observer, it looks like the black hole is glowing, slowly evaporating. And the smaller the black hole, the faster it evaporates. A black hole the size of a Planck length would radiate so intensely it would vanish in less than a Planck time. It would be a flash, a spark, a moment so brief it barely qualifies as existence. This tells us something profound. Gravity and quantum mechanics don't just clash at the Planck scale. They create entirely new phenomena, black holes that glow, space-time that foams, particles that borrow existence from the void and return it before anyone notices. These aren't glitches in the theory, they're predictions. Strange, untestable, beautiful predictions. And they all point to the same conclusion. At the smallest scales, the universe is not what we think it is. Here's a question worth sitting with. If space-time itself is uncertain, what does that mean for the notion of cause and effect? We're used to thinking of events in a sequence. This happens then, that happens. Cause leads to effect. Time flows forward. But if time is grainy, if it ticks forward in Planck-sized jumps, or if it foams and churns at the smallest scales, does causality still hold? Can effects still follow causes if the fabric connecting them is unstable? Some physicists think causality might be an emergent property too, something that only makes sense at larger scales when the foam averages out into smoothness. At the Planck scale, cause and effect might blur into a quantum haze where events don't happen in order they happen in superposition all at once and never. It's dizzying, but it's also honest. The truth is, we don't know what happens when gravity meets quantum mechanics. We have theories. String theory suggests that particles aren't points but tiny vibrating strings, and that space-time has extra dimensions curled up at the Planck scale. Loop quantum gravity suggests that space is woven from discrete loops and time advances in quantum jumps. Both are mathematically elegant. Both make predictions. But neither has been proven. They're educated guesses whispered in the language of mathematics, waiting for nature to whisper back. And maybe that's okay. Maybe the Planck scale is meant to remain mysterious. Not because we're not smart enough to understand it, but because understanding itself requires a framework, a language, a set of concepts like space-time, position, momentum. And at that scale, those concepts lose their meaning. It's not ignorance. It's the edge of what language can describe. like trying to paint silence or write the taste of water. Some things exist beyond words. What we do know is this: the Planck scale is the border, the frontier, the place where the two great theories of the 20th century reach out and touch, and in touching, reveal their limits. Neither is wrong, both are incomplete, and somewhere in the gap between them, in the space where gravity and quantum mechanics collide, the true nature of reality hides. Quiet, patient, waiting for us to find the right question. So, we've seen the numbers, we've watched the theories collide, but there's more strangeness ahead, deeper still. Because if space-time can foam, if it can bubble and twist, what does that foam look like up close? What lives in those quantum bubbles? What geometry forms when space itself forgets how to be smooth? The answer is stranger than math, stranger than metaphor. It's a vision of reality as a sea churning in the dark. Imagine standing at the edge of the ocean on a windy day. From a distance, the water looks smooth, a single blue surface stretching to the horizon. But step closer. Watch the waves. See how they rise and crash, how foam gathers in the troughs, how the surface churns and bubbles. Now, imagine shrinking down smaller and smaller until you're the size of a water molecule. The ocean isn't smooth anymore. It's chaos. Molecules colliding, swirling, forming temporary clusters that dissolve the instant they appear. The stillness was an illusion. Up close, everything moves. At the Planck scale, space-time is that ocean. And we're only beginning to see the foam. The idea didn't come from mathematics alone. It came from a man who thought in pictures. John Archibald Wheeler was born in 1911 in Jacksonville, Florida. He studied under Niels Bohr, worked with Einstein, and spent his life asking questions most physicists avoided. Questions like, what is space-time made of? Is it a thing or just a stage? Can it break? Can it breathe? In the 1950s, while most of his colleagues were refining quantum mechanics or testing relativity, Wheeler was imagining what would happen if you zoomed in far enough. If you looked at the fabric of reality not with telescopes or microscopes, but with pure thought. And what he saw disturbed him. He saw foam. Wheeler called it quantum foam, sometimes space-time foam. The name sounds soft, almost playful, like something you'd find in a child's bath. But the reality it describes is anything but gentle. At scales approaching the Planck length, Wheeler proposed space-time doesn't behave like a smooth sheet. It writhes, it twists, it bubbles with energy. Tiny wormholes smaller than atoms flicker into existence and vanish in less time than it takes light to cross them. The geometry of space, that stable grid we trust to hold the universe together, becomes unstable, uncertain, foaming. Why would space behave this way? The answer lies in Heisenberg's uncertainty principle, one of the strangest rules in quantum mechanics. It says that you can't know both the position and momentum of a particle with perfect precision. The more accurately you measure one, the less you know about the other. But the principle doesn't just apply to particles. It applies to energy and time as well. The shorter the time interval you examine, the greater the uncertainty in energy. And at the Planck time scale, 10 to the negative 44 seconds, that uncertainty becomes enormous. Here's what that means. In any tiny region of space, even in what we call the vacuum, energy is constantly fluctuating. Virtual particles, pairs of matter and antimatter, pop into existence, borrow energy from the void, and annihilate each other before the universe can notice the debt. These fluctuations are real. We've measured them indirectly through something called the Casimir effect, where two metal plates placed very close together in a vacuum experience a measurable force because fewer virtual particles can fit between them than outside. The vacuum isn't empty. It hums with invisible activity. But energy, according to Einstein, curves space-time. Mass and energy are equivalent two faces of the same coin. So, if the vacuum is seething with fluctuating energy, space-time itself must fluctuate. At ordinary scales, these fluctuations are so tiny we never notice them. Space looks smooth because we're too large, too slow to see the trembling underneath. But at the Planck scale, the fluctuations dominate. The smooth fabric tears into a froth of quantum geometry. Distances lose meaning. Straight lines curve. Cause and effect tangle. The universe at its smallest is not solid ground. It's a storm. Wheeler tried to describe what this foam might look like. He imagined space-time at the Planck scale as a tangled network of wormholes, tiny tunnels connecting different points in space, opening and closing faster than measurement could follow. In his vision, a single cubic Planck length of space might contain billions of these micro wormholes threading through dimensions we can't see, creating a topology so complex that the word shape loses its grip. He once said it would look like a piece of bread dough, kneaded and stretched full of air pockets and folds, except the dough is the fabric of reality, and the folds lead to places that might not even exist in our 3 dimensions. It's a dizzying thought, but Wheeler wasn't alone. Other physicists approaching the problem from different angles arrived at similar conclusions. In the 1960s, Soviet physicist Matvei Bronstein, working independently, suggested that quantum effects would make space-time unstable at small scales. He was executed during Stalin's purges before he could finish his work, but his ideas survived. Later, researchers studying loop quantum gravity, a theory that tries to merge relativity with quantum mechanics, found that their equations also predicted a grainy, discrete structure to space. Not smooth, not continuous, but woven from threads, loops of quantum information smaller than anything we can name. Here's a way to visualize it, though, imperfectly. Imagine the surface of a calm pond. From above it looks glassy, reflective still. But if you could zoom in to the molecular level, you'd see water molecules jittering, bumping into each other, forming temporary bonds that break and reform constantly. The stillness is a statistical illusion, an average taken over billions of molecules. Quantum foam is similar. From our scale, space-time looks smooth because we're averaging over an unimaginable number of Planck scale fluctuations. But zoom in and the stillness shatters. The pond becomes a boil. Now you might ask, if space-time is foaming at the smallest scales, why don't we notice? Why doesn't the universe feel unstable? The answer is scale. The Planck length is so incomprehensibly small that its fluctuations have almost no effect on anything larger. It's like trying to feel the vibration of individual atoms in a steel beam. The beam feels solid because you're made of trillions of atoms and their individual jitters average out. Similarly, we move through space-time in chunks vastly larger than the Planck scale. The foam is there churning beneath us, but we glide over it like a ship over a rough sea. We feel the swell maybe in certain rare effects, but we never see the white caps. Still, some researchers believe the foam might leave traces, tiny, almost undetectable signatures. For instance, light traveling across vast distances through space might interact with the foam, scattering, slightly blurring its path. Gamma ray bursts, the most energetic explosions in the universe, send light racing toward us across billions of light years. If space-time is foamy, that light might arrive with a slight fuzziness, different wavelengths delayed by infinitesimal amounts. Scientists have looked. So far, they've found nothing conclusive. Either the foam is too subtle or it doesn't exist in the way we imagine. Either way, the search continues. One of the most beautiful aspects of quantum foam is how it reframes our understanding of emptiness. We think of the vacuum as nothing, absence, void. But quantum mechanics says the vacuum is full. It's not empty space. It's the lowest energy state, and even that state seethes with activity. Virtual particles, fluctuating fields. And now, if Wheeler and others are right, fluctuating geometry. The vacuum is alive in a way that defies intuition. It's not a place where nothing happens. It's a place where everything happens briefly in superposition too fast for the universe to register. Think about that. Every point in space, even in the darkest, coldest, most isolated regions between galaxies, is trembling with potential. Not potential energy we can harvest. Not potential in a practical sense, but potential in a deeper way. The potential for structure, for connection, for meaning. Wormholes that go nowhere. Particles that exist for less than an instant. Distances that can't be measured because they're smaller than measurement itself. The foam is a reminder that reality is not a thing. It's a process, a constant becoming, a dance between being and not being, happening everywhere all the time invisibly. Here's where it gets even stranger. Some physicists speculate that the foam might explain the cosmological constant problem, one of the biggest unsolved puzzles in physics. The cosmological constant measures the energy density of empty space, what we call dark energy. Observations show it's tiny, but quantum field theory predicts it should be enormous, 120 orders of magnitude larger than what we observe. That's not a small error. It's the worst prediction in the history of science. Why is the vacuum energy so much smaller than expected? Some believe the answer lies in the foam. Perhaps the violent fluctuations at the Planck scale somehow cancel out, averaging to nearly zero. Perhaps the foam regulates itself, smoothing its own turbulence through mechanisms we don't yet understand. It's speculation, but it's elegant speculation. There's also a philosophical weight to the idea of quantum foam. It suggests that space and time, the two things we consider most fundamental, most solid, are themselves emergent. They arise from something deeper, something more primal. Just as temperature emerges from the motion of molecules, space-time might emerge from the interactions of quantum foam. Below the foam, there might be no space, no time, no geometry, just information, just relationships, just pure mathematics playing out in a realm where the question where and when have no meaning. We don't know what that realm is. We only know it must exist hidden beneath the foam, holding everything together. Wheeler once said that the universe is a participatory phenomenon, that observers through the act of measurement help to create reality. He wasn't being mystical. He was following the logic of quantum mechanics to its conclusion. If space-time is foamy, if it's fundamentally uncertain, then the act of observation of choosing what to measure might collapse the foam into a specific configuration. Reality in this view isn't something we discover. It's something we participate in creating, not in a solipsistic way, but in a deep quantum way where the observer and the observed are entangled at the most fundamental level. It's humbling and a little unnerving. To think that the ground beneath our feet, the space between stars, the time that ticks forward, all of it might be a kind of illusion, not false but approximate, a smoothed-out version of something wilder, something that only reveals itself at scales we can never touch. The foam is there, always churning in the dark. We live on its surface, building our theories, measuring our constants, mapping our universe. But beneath the map, the territory is foaming. And perhaps that's okay. Perhaps the foam is a gift, a reminder that certainty is not the goal, that the universe is deeper than we can fathom, that beneath every answer lies another question, and beneath that question, another mystery. The foam doesn't close doors, it opens them, into places we can't go, into ideas we can't yet speak, but we can imagine them. We can wonder. And in wondering, we touch the edge of something vast. So, space-time foams, it bubbles, it churns. At the smallest scales, reality is not a stage, but a sea. And we've only just begun to listen to its rhythm. But there's another way the Planck scale breaks reality. Another place where the foam condenses into something even stranger. A place where gravity becomes so strong that space itself collapses into a point. A place where time ends. We call them black holes. And at the Planck scale, they are the strangest things of all. There are objects in the universe so dense that they swallow light, so heavy that they bend time until it stops. We call them black holes, and for most of human history, they were impossible. A mathematical ghost, A prediction too strange to be real, but they are real. We've photographed them, watched stars orbit them, listened to them collide. Yet even now, after a century of study, black holes remain deeply mysterious. And at the Planck scale, where black holes shrink to their smallest possible size, they become something else entirely, not objects, not even holes, just whispers of existence flickering at the edge of meaning. The story begins, as many strange stories do, with Carl Schwarzschild. In 1915, only months after Einstein published general relativity, Schwarzschild was serving in the German army on the Russian front during World War I. Between artillery barrages and the frozen trenches, he solved Einstein's equations exactly. What he found shocked him. The equations predicted that if you compressed enough mass into a small enough space, space-time would curve so sharply that nothing, not even light, could escape. A boundary would form an event horizon, inside which the future points only inward. Schwarzschild sent his solution to Einstein, who was both impressed and uneasy. He didn't believe such objects could actually exist. Nature, he thought, would find a way to prevent them. He was wrong. For decades, black holes remained theoretical curiosities. Then, in the 1960s, astronomers began finding strange sources of X-rays in space. Objects too massive to be stars, too small to see pulling matter from companion stars and heating it to millions of degrees before swallowing it whole. Slowly, the evidence mounted. Black holes were real, and they came in sizes. Stellar mass black holes a few times heavier than the sun formed from collapsed stars. Supermassive black holes, millions or billions of solar masses lurking at the centers of galaxies. And in theory, much smaller ones. Primordial black holes perhaps created in the turbulence of the early universe. And at the very bottom of the scale, something almost mythical: Planck black holes. A Planck black hole is a black hole with a mass equal to the Planck mass, about 22 micrograms, the weight of a flea's egg, but compressed into a volume the size of the Planck length. Imagine that, a speck of mass smaller than an atom, but so dense that its gravity warps space-time into a singularity. According to the equations, such an object can exist, at least mathematically. But if it did, it wouldn't last. Because black holes, as Stephen Hawking discovered in 1974, are not eternal. They glow, they evaporate, and the smaller the black hole, the faster it dies. Hawking's discovery was revolutionary. He showed that quantum effects near the event horizon cause black holes to emit radiation, now called Hawking radiation. The mechanism is subtle. Virtual particle pairs, those temporary fluctuations in the quantum vacuum, pop into existence near the horizon. Normally, they annihilate each other immediately. But near a black hole, one particle can fall in while the other escapes. To an outside observer, it looks like the black hole is radiating. And because energy is conserved, the black hole loses mass with every particle that escapes. It shrinks, slowly at first. But as it shrinks, it gets hotter, radiates faster, shrinks faster still. A runaway process, a death spiral. For a stellar mass black hole, this process takes an unimaginable amount of time. A black hole with the mass of the sun would take 10 to the 67 years to evaporate, longer than the current age of the universe by a factor so large it's meaningless. But a Planck black hole research shows it would evaporate in about 10 to the negative 43 seconds. One Planck time. It would exist for the shortest possible duration, and then vanish in a burst of energy so intense it would rival the Big Bang in temperature. Not an explosion you could see, an explosion that would happen and unhappen in less time than time itself can measure. A flicker at the boundary of existence. Here's what makes this so strange. A Planck black hole sits exactly at the threshold, where quantum mechanics and gravity have equal strength. It's the only object in nature, real or theoretical, where the two forces meet on perfectly balanced terms. Larger black holes are dominated by gravity. quantum effects are negligible. Smaller objects, if they could exist, would be dominated by quantum mechanics. Gravity would barely matter, but a Planck black hole is both, fully quantum, fully gravitational. It's the Rosetta Stone of physics, the key to understanding how the two theories might unify. Except, we can't study it. It exists for less than an instant, and we have no way to create one. Or do we? In the early 2000s, when the Large Hadron Collider was being built, some physicists speculated half seriously that it might produce microscopic black holes, not dangerous ones. Tiny ones far smaller than atoms that would evaporate instantly in bursts of Hawking radiation. The idea was that if space has extra dimensions curled up at small scales, gravity might become much stronger than we think. And at high enough energies, particle collisions might concentrate enough mass into a small enough space to form a black hole. The LHC never created one, as far as we know. But the fact that we even considered it shows how close we are to the Planck scale conceptually, if not practically. We're probing energies where the rules start to bend. Now, let's talk about what happens inside a Planck black hole. Or rather, what might happen, because honestly, we don't know. The interior of any black hole is hidden behind the event horizon, a one-way membrane where time and space swap roles. Once you cross it all, paths lead inward, not because you're being pulled, but because the geometry of space-time itself points only toward the singularity. At the center of a black hole, general relativity predicts a point of infinite density, a singularity, a place where the equations break down and spit out infinities. Most physicists believe singularities are not real. They're signs that our theory is incomplete, that something else, some quantum effect, must smooth out the infinite curvature before it becomes truly infinite. But inside a Planck black hole, there is no inside. The entire black hole is smaller than the Planck length. The event horizon, the singularity, the curved space-time, between them, all of it exists in a region where the concepts of distance and duration lose meaning. You can't ask what's inside because there's no room for inside. It's not a place. It's a knot in space-time, a tangle so tight that geometry itself gives up. Some theorists suggest that Planck black holes might not have singularities at all. Instead, they might be stable quantum objects, little bubbles of curved space that exist for a moment and then pop. Not because they evaporate, but because they were never fully classical to begin with. This raises a haunting question. If Planck black holes exist at the boundary where space-time becomes uncertain, are they the same as the quantum foam we discussed earlier? Are the wormholes? Wheeler imagined those tiny tunnels threading through the vacuum, actually microscopic black holes blinking in and out of existence. Some physicists think yes, that the quantum foam is a sea of Planck black holes forming and dissolving, faster than measurement stitching, space-time together at the smallest scales. It's a beautiful idea. Unproven, but beautiful. It suggests that black holes are not exotic anomalies. They're fundamental, woven into the fabric of reality from the very beginning. Let's pause and consider the temperature of a Planck black hole. Hawking showed that the temperature of a black hole is inversely proportional to its mass. The smaller the black hole, the hotter it gets. A solar mass black hole has a temperature of about 60 nanokelvins, far colder than the cosmic microwave background. It absorbs more radiation than it emits. But a Planck black hole would have a temperature equal to the Planck temperature, 1.4 times 10 to the 32 Kelvin, hotter than anything that has existed since the first moments of the Big Bang. At that temperature, particles don't just move fast, they cease to have identity. Quarks, electrons, photons, all distinctions blur. Matter and energy become one roiling plasma where the rules of particle physics dissolve. A Planck black hole in its final instant would be the hottest thing in the universe. And then it would be gone. There's a paradox here, a lesson maybe. The smallest black holes are the hottest, the briefest, the most energetic. they pack the most intensity into the least time. It's as if the universe is saying that existence at its most compressed burns brightest. That meaning doesn't require duration. That a moment, if it's extreme enough, can contain more reality than eons of calm. A Planck black hole lives and dies in less than a blink. But in that unblink, it touches the absolute limits of temperature density and energy. It experiences everything the universe allows. And then it vanishes, leaving nothing but a faint ripple in the vacuum. Now, here's where it gets philosophical. Some researchers believe that the Big Bang itself might have been a kind of Planck black hole in reverse. Imagine the entire universe, all its mass and energy compressed into a volume the size of the Planck length. At that scale, the distinction between a black hole and a universe blurs. The event horizon becomes the boundary of reality. Time, instead of ending at the singularity, begins there. The Big Bang in this view is not an explosion in space, it's an explosion of space. A Planck black hole turning itself inside out, radiating not particles but dimensions, not heat but time. It's speculative, wildly so, but it's also elegant. It connects the smallest possible black hole to the largest possible event. The Planck scale as both the end and the beginning. There's also the information paradox, one of the deepest puzzles in modern physics. When a black hole evaporates, where does the information about the matter that fell in go? Quantum mechanics says information can't be destroyed. But if a black hole radiates purely thermal radiation, random heat with no structure, the information seems lost. Hawking wrestled with this for decades. He initially believed information was destroyed, that black holes were the universe's erasers. But later, he changed his mind. He suggested that information might be encoded in the Hawking radiation itself, in correlations too subtle to detect. The debate continues. And Planck black holes, because they evaporate so quickly, might hold the key. If information can escape a Planck black hole in one Planck time, maybe the mechanism is simpler than we think, or maybe it's stranger. Think about what this means for the nature of reality. If black holes preserve information, then nothing is ever truly lost. Every particle that falls past an event horizon leaves a trace encoded somewhere in some form. The universe keeps records. Even in the most extreme conditions, even at the Planck scale where space and time dissolve, there's a memory, a continuity. It's oddly comforting. The idea that the cosmos doesn't forget, that meaning persists even in the dark. But let's be honest, we don't know if Planck black holes exist. We've never seen one. We can't create one. We can only calculate them, dream them, imagine them through the lens of equations that might be wrong. They live in the gap between general relativity and quantum mechanics, in the space where both theories shout different truths. Maybe Planck black holes are real. Maybe they're the seeds of space-time the foam made manifest. Or maybe they're mathematical artifacts, beautiful but empty. Either way, they teach us something. They show us the edge, the place where our understanding thins, where confidence turns to wonder. And maybe that's enough, to know there's an edge, to feel the vertigo of standing near it, to realize that the universe has secrets it might never share, not because we're unworthy, but because some questions exist beyond answering. Planck black holes are one of those questions. Are they real? Are they the smallest, the hottest, the briefest we can ask? We can calculate, but we might never know. And in the not knowing, there's a strange kind of peace. So black holes, even at the Planck scale, remain mysterious. They glow with impossible heat. They evaporate in impossible time. They hold information or they don't. They exist or they're ghosts. But either way, they point us somewhere deeper, somewhere older. Because if Planck black holes mark the smallest things that can be, then there's a question about the first thing that was. The moment when the universe itself was Planck-sized. The instant before time had meaning. That moment has a name, and it too is strange beyond words. Every story has a beginning, the first word, the first breath, the first light breaking over a dark horizon. We crave origins. We ask where things come from, how they started what came before. And for the universe itself, the answer seems clear: the Big Bang. 13.8 billion years ago, everything that is was compressed into a single point, infinitely hot, infinitely dense, and then it exploded, expanded, cooled, formed stars and galaxies, and eventually us. But that story, as clean as it sounds, has a gap, a silence, a moment we cannot describe, the first 10 to the negative 43 seconds, the Planck epoch. Before that instant, we have no physics, no equations, no language. And if time itself didn't exist yet, can we even call it before? The Big Bang Theory is one of the triumphs of 20th century science. It began with Edwin Hubble's observations in 1929, when he discovered that distant galaxies are moving away from us, and the farther they are, the faster they recede. The universe is expanding. If you run that expansion backward, rewinding time like a film, everything converges. Galaxies collapse into each other. Stars dissolve into gas. Gas compresses into pure energy. And eventually, you reach a point where all the matter and energy in the universe occupied a volume smaller than an atom, a singularity, the moment of creation. But singularities make physicists uncomfortable. They represent places where the math breaks down, where quantities become infinite, where predictions lose meaning. General relativity, the theory that describes the Big Bang, works beautifully for most of cosmic history. It explains how the universe expanded, how matter clumped into structures, how light stretched into the microwave background we still detect today. But as you approach the very first moment as the universe shrinks to subatomic sizes, relativity falters. Because at those scales, quantum mechanics takes over, and the two theories, as we've seen, don't play well together. This is where the Planck time enters. 5.39 times 10 to the negative 44 seconds after the Big Bang, the universe was still unimaginably small and hot, but it had grown large enough, cool enough, that our equations begin to make sense. Space and time, though still wildly curved and energetic, had meanings we can describe. Before that, before the Planck time, we don't know. Our physics goes silent, not because the instruments fail, but because the concepts themselves, space-time causality, might not have existed in any form we recognize. Scientists suggest that at the Planck epoch, the universe was smaller than the Planck length. Its temperature was at or above the Planck temperature. Its density was so extreme that quantum fluctuations in space-time were as large as space-time itself. Imagine trying to measure the size of a room while the walls are vibrating faster than you can see, shifting in and out of existence. That's what the early universe was like. Not a room, not even a point. A boiling knot of energy and geometry, where the distinction between here and there, between now and then, dissolved completely. Here's the really strange part. Time as we experience it is the ordered sequence of events. One thing happens, then another, then another. Cause precedes effect. Memory points backward. Future points forward. But at the Planck epoch, this sequence might not have existed. Quantum mechanics allows for superpositions, states where multiple possibilities exist simultaneously. Some cosmologists believe that in the first Planck time, the universe existed in a superposition of all possible states, not one timeline, but many overlapping, interfering, not yet collapsed into the single history we observe. Time in that view didn't flow, it shimmered. A quantum haze of potential moments, none more real than the others. There's a common misconception that the Big Bang was an explosion in space, that there was a void and then suddenly matter and energy burst into it. But that's not right. The Big Bang was an explosion of space. Space itself expanded. There was no outside for it to expand into. And before the Planck time, there might not have been an inside either. The universe wasn't a tiny ball floating in darkness. It was all there was. And all there was might not have had dimensions, boundaries, or duration. Just potential. just mathematics waiting to become real. Let's try an analogy. Imagine a frozen lake. The surface is smooth, solid, ordered. You can walk on it, measure it, map it. That's space-time after the Planck epoch. Now, imagine the lake melting the ice, breaking into slush water, and solid mixed together, no clear boundary between them. That's space-time at the Planck epoch. Now, imagine the lake before it froze. Just water flowing shapeless, no structure at all. That might be what existed before Planck time. Not space, not time. Just the raw ingredients waiting for conditions to crystallize them into something we can call a universe. One of the leading ideas about what happened before Planck time is called quantum cosmology. It suggests that the universe didn't have a beginning in the traditional sense. Instead, it emerged from a quantum state, a timeless realm where the concept of before has no meaning. Stephen Hawking and James Hartley proposed something called the no-boundary proposal in the 1980s. They imagined time near the Big Bang as being like the surface of the Earth. If you travel south, you eventually reach the South Pole, but there's no edge, no boundary, no point where south stops making sense. Similarly, as you travel backward in time toward the Big Bang, time gradually becomes space-like. The distinction blurs. The question, what came before, becomes like asking, what's south of the South Pole? Grammatically correct. Conceptually empty. It's a dizzying idea, but it resolves a problem. If time itself began at some point, what caused it to begin? A cause requires time. So asking what caused the Big Bang is asking what came before time, which is incoherent. But if time didn't begin, if it simply is woven into the geometry of the universe in a way that has no edge, no start, then the question dissolves. There's no before. There's only the eternal present of space-time curved back on itself in ways that create the illusion of a beginning when viewed from within. Other theories take different approaches. Loop quantum cosmology suggests that the Big Bang wasn't the beginning, but a bounce, that the universe has been cycling forever, expanding, contracting, bouncing at the Planck scale, expanding again. In this view, the Planck epoch is not the origin, but a transition, a moment when the universe was at its smallest and hottest before rebounding into the expansion we observe. The contraction phase, the universe before the bounce, existed in a quantum state so dense that space and time were granular, made of discrete loops of geometry. At the bounce, those loops stretched, smoothed out, and became the continuous space-time we know. Then there's the idea of eternal inflation proposed by physicists like André Linde and Alan Guth in the early 1980s. Inflation is the theory that the universe in its first fraction of a second expanded exponentially fast, smoothing out irregularities and setting the stage for the slower expansion we see today. But eternal inflation suggests that this inflationary phase never completely ends. In some regions, inflation stops, and a universe like ours forms. In other regions, inflation continues spawning new universes which spawn more forever. Our Big Bang in this scenario is just one bubble in an infinite multiverse. And the Planck epoch, it's the moment when our bubble nucleated, when a tiny patch of inflating space decided to stop and become a cosmos. These ideas, quantum cosmology, the Big Bounce, eternal inflation, they're all speculative. We have no direct evidence for any of them, but they share a common thread. They all suggest that the Planck epoch is the boundary of our knowledge, not because we lack data, but because the questions we ask on this side of the boundary might not apply on the other side. It's like trying to use a map of the ocean to navigate the sky. The tools don't fit. The language doesn't translate. Here's a question that haunts cosmologists. Did time have a first moment, or has it always existed stretching infinitely into the past? Both possibilities feel wrong. If time had a first moment, what set it in motion? If time is infinite, how did we ever arrive at now? The Planck epoch sits at the center of this paradox. It's the moment when time as we understand it becomes describable. Before that, maybe time was something else. Maybe it was imaginary in the mathematical sense, a dimension that behaved like space. Maybe it was probabilistic, a cloud of possible durations. Maybe it wasn't at all. One of the mistakes people make is thinking that the Big Bang happened at a point in space. It didn't. It happened everywhere. Every point in the universe today was 13.8 billion years ago, part of that hot, dense state. The Big Bang wasn't an event you could point to. It was a condition, a state. And as you trace that state backward, as the universe shrinks, the density and temperature rise, you approach the Planck epoch. At that moment, every point in space was closer to every other point than the Planck length. The universe was so small that the concept of point lost meaning. There were no separate locations, just a unified, undifferentiated wholeness. Think about the temperature. The Planck temperature, 10 to the 32 Kelvin. The early universe reached that temperature, or something close, in the first Planck time. At that heat, particles didn't just move fast. They didn't exist as particles. Matter and energy were indistinguishable. The four fundamental forces, gravity, electromagnetism, the strong and weak nuclear forces, they might have been unified. A single force, a single field. Physicists call this the theory of everything, and we don't have it yet. But if it exists, it would describe the Planck epoch. The moment when the universe was so simple, it was perfectly symmetric. No distinction between forces, no distinction between particles, just pure energy singing at the highest note the cosmos allows. As the universe expanded and cooled, that symmetry broke. First gravity separated, then the strong nuclear force, then the electromagnetic and weak forces split apart. Each breaking released energy shaped the structure of space-time, set the stage for complexity. Matter formed, atoms formed, stars formed, us. But in the Planck epoch before the breaking, there was unity. And some physicists believe that understanding that unity, describing it mathematically, is the ultimate goal of theoretical physics. Not to control it, not to recreate it, just to know. To see if only in equations what the universe looked like when it was one. There's something poetic in this. The idea that the universe began in perfect simplicity and has been complexifying ever since. That the chaos we see, the diversity, the endless forms are all echoes of a single elegant state that existed for less than 10 to the negative 43 seconds. It's like a piece of music. The first note is pure, unadorned, and then it branches, harmonizes, weaves into a symphony. The Planck epoch is that first note. We can't hear it. It's too brief, too high, too far in the past. But we can infer it. We can feel its resonance in everything that came after. So did time exist before the Planck time? The honest answer is, we don't know. Maybe time is eternal, looping back on itself in ways we can't picture. Maybe it began in a quantum fluctuation, a random event in a timeless void. Maybe it emerged gradually, crystallizing out of a more fundamental geometry. Or maybe the question itself is wrong. Maybe before is a word that only works within time, and asking what came before time is like asking what color the number 7 is. Not a hard question, a nonsense question. But here's what we do know. The universe had a Planck epoch, a moment so extreme, so compressed that all our descriptions fail. And in that failure, there's a kind of grace, because it means the universe still has secrets, places our minds can't quite reach. Frontiers not just of knowledge, but of knowability. And that's okay. Maybe it's even beautiful to stand at the edge of time and realize that the edge is real, that there are boundaries built not by ignorance, but by the structure of reality itself. We've traced the universe back to its first describable instant. But there's another boundary ahead equally strange, the boundary of what we can see. Because even if we had infinite knowledge, perfect equations, flawless theories, there's a limit to what we can observe. The Planck scale is not just hidden by math, it's hidden by nature. And the reasons why the mechanisms that keep it locked away are about to reveal something profound about the universe's design. There are frontiers humanity has crossed. We've split the atom, photographed black holes, sent machines beyond the solar system. We've peered into the heart of matter and traced light from the edge of the observable universe. But there is one frontier we will never cross. Not because we lack the will or the funding or the time, but because nature herself has placed a lock on it. A quiet, absolute prohibition written into the laws of physics. We can calculate the Planck scale. We can imagine it, but we will never see it. Not with telescopes, not with microscopes, not with any instrument we could ever build. And the reasons why tell us something profound about the limits of knowledge itself. Let's start with what it would take to observe the Planck scale. To see structure at the Planck length, you need to probe it with something small enough to fit. Light, for instance. The wavelength of light determines how small a feature it can resolve. Visible light has a wavelength of about 500 nanometers. That's why you can't see individual atoms with your eyes. Atoms are far smaller than the wavelength of visible light. To see atoms, you need shorter wavelengths. X-rays with wavelengths around 0.1 nanometers can reveal atomic structures. Electron microscopes using beams of electrons with even shorter wavelengths can image individual atoms with startling clarity. But to see the Planck length 10 to the negative 35 meters, you'd need a wavelength that small, and the wavelength of light is inversely related to its energy. Shorter wavelength means higher energy. A photon with a wavelength equal to the Planck length would carry an energy equal to the Planck energy. That's about 2 billion joules, the energy of a lightning bolt, the energy of an exploding hand grenade, packed into a single photon. And here's the problem. If you concentrate that much energy into a region the size of the Planck length, you don't just illuminate what's there, you destroy it. You create a black hole. This isn't speculation. It's a direct consequence of general relativity and quantum mechanics. The Schwarzschild radius, the size of the event horizon for a black hole of a given mass, is proportional to that mass. For a Planck mass compressed into a Planck length, the Schwarzschild radius is exactly the Planck length. The object you're trying to observe and the black hole you'd create by observing it are the same size. The act of measurement becomes the act of annihilation. You can't see the Planck scale because seeing requires energy, and that energy warps space-time so violently that it collapses into a singularity. The universe won't let you look. Scientists describe this as a kind of cosmic censorship, not in the political sense, but in the physical sense. Nature hides her deepest workings behind an event horizon. The Planck scale is the ultimate black box. We can study its effects, we can infer its properties, but we can't open it, we can't peer inside, and no future technology, no matter how advanced, will change that. Because the limit isn't technological, it's ontological. It's built into the structure of reality. Let's make this concrete with numbers. The Large Hadron Collider, the most powerful particle accelerator ever built, smashes protons together at energies around 13 trillion electron volts. That sounds enormous. And it is by human standards. But the Planck energy is about 10 to the 19th times higher. To build a collider capable of reaching Planck energy, you'd need a ring roughly the size of the Milky Way galaxy. And that's just the circumference. The energy requirements would dwarf the entire power output of the sun. You'd need to harness the energy of stars, channel it through superconducting magnets, and somehow keep the whole system stable while accelerating particles to energies where space-time itself becomes uncertain. It's not impossible because we lack the engineering. It's impossible because the universe doesn't have enough accessible energy in any practical sense. Here's another way to think about it. Imagine you wanted to build a microscope capable of resolving the Planck length. You'd need to probe something to interact with the thing you're observing. Let's say you use a photon. To get the wavelength down to Planck scale, that photon would need Planck energy. But photons don't just passively observe, they carry momentum. When they hit something, they transfer energy. A Planck energy photon hitting a particle would impart so much momentum that the particle would be accelerated to nearly the speed of light, if it didn't immediately disintegrate into a shower of other particles or collapse into a black hole. You wouldn't be observing the system, you'd be obliterating it. This is the essence of the Heisenberg uncertainty principle taken to its extreme. The more precisely you try to measure position, the more you disturb momentum, and vice versa. At the Planck scale, this disturbance isn't a minor inconvenience. It's total. Measurement and destruction become indistinguishable. The observer and the observed cannot be separated. Knowledge at that level is self-negating. There's a philosophical weight to this. For centuries, science has been built on the assumption that with enough cleverness, enough resources, we can observe anything. That the universe is in principle fully knowable. That mysteries are just puzzles waiting to be solved. But the Planck scale says no. Some mysteries are protected, not by our ignorance, but by the laws of physics themselves. There is a boundary, and it's not movable. It's etched into the fabric of existence. And standing at that boundary, we have to accept that some questions might never have observable answers. Let me give you an analogy. Imagine you're trying to read a book, but the only light source you have is a flamethrower. The moment you illuminate the page, you incinerate it. The act of trying to see destroys the thing you're trying to read. That's what probing the Planck scale is like. The tool required to observe it is the same tool that erases it. You can't have both. You can't measure without destroying. And so, the text remains unread, not because the letters aren't there, but because reading them is fundamentally impossible. Now some might ask, couldn't we find indirect ways to study the Planck scale? Look for its effects on larger scales like ripples spreading from a stone dropped in a pond. In theory, yes. And scientists have tried. For instance, if space-time is grainy at the Planck scale, light traveling across vast distances might scatter slightly like sunlight, filtering through a foggy window. High-energy photons from distant gamma-ray bursts, which have traveled billions of light-years, might show tiny delays or distortions. Researchers have looked. They've analyzed the light from some of the most distant, most energetic events in the universe, and so far they've found nothing. Either the effect is too small, or space-time is smoother than we thought, even at the Planck scale. Either way, the Planck realm stays hidden. There's also the question of quantum gravity experiments. Some physicists have proposed clever setups involving ultra-cold atoms laser interferometry, or quantum entanglement, to test predictions about how gravity behaves at tiny scales. But these experiments don't probe the Planck scale directly. They probe regimes where quantum effects and gravity both matter, but are still many orders of magnitude larger than Planck length. It's like trying to understand the ocean by studying a puddle. Useful maybe, but not the same. Here's a thought that haunts some researchers. What if the Planck scale isn't just observationally inaccessible? What if it's conceptually inaccessible? What if the very act of asking, what happens at the Planck scale, is asking a question that doesn't have a meaningful answer, like asking what's north of the North Pole, or what happened before time began. Some theories suggest that space and time might be emergent, properties, things that only exist at larger scales. And below the Planck length, there's no space or time, just some more fundamental substrate we don't have words for. In that case, observing the Planck scale would be like trying to see the pixels in a photograph from inside the photograph. The pixels aren't places you can visit. They're the building blocks of place itself. This leads to a humbling realization. The Planck scale might be the absolute limit of empirical science. Empirical means testable, observable, verifiable through experiment. But if the Planck scale can't be tested, if it lies forever beyond the reach of any possible experiment, then our knowledge of it will always be theoretical. We can propose models, write equations, make predictions, but we can never check them against reality in the way science usually demands. We're left with mathematics, beautiful and elegant, but unverifiable. And that's strange, because it means there's a part of the universe, a real physical part, that might be forever sealed off from the scientific method. Does that make the Planck scale unreal? No, just unobservable, like the interior of a black hole. We know black holes exist. We can see their effects, watch stars orbit them. detect gravitational waves when they merge, but we can't see inside the event horizon. The information is locked away. Similarly, the Planck scale shapes everything. It sets the limits on temperature density, the earliest moments of the universe. Its fingerprints are everywhere. But the thing itself, the actual geometry of space-time at that scale, remains invisible, a ghost in the machine. Let's talk about energy costs in a more visceral way. The total energy humanity uses in a year is about 580 exajoules. That's all the electricity, all the fuel, all the power generated by every power plant, car, and device on Earth. The Planck energy. The energy needed to probe one Planck-length region of space is about 2 billion joules. Doesn't sound so bad, right? But here's the catch. To actually explore the Planck scale meaningfully, you need to create not just one Planck energy event, but many. Billions. Trillions. Because one observation tells you almost nothing. You need statistics, repeatability, control. And even if you somehow harness the entire energy output of the sun for 1 million years, you still wouldn't have enough to run a single meaningful experiment. The scales don't just mismatch, they're incommensurable. There's a lesson here about human ambition. We've achieved so much. We've decoded DNA, landed on the moon, imaged atoms, listened to the echo of the Big Bang. Each achievement pushed the frontier a little farther. And it's easy to assume that progress will continue forever, that every mystery will eventually yield. But the Planck scale teaches us otherwise. It teaches us that there are hard limits, that the universe has secrets it will never share, not because we're not smart enough, but because the asking itself violates the rules. It's a kind of cosmic modesty, a reminder that we are small, finite creatures in a vast layered reality, and some of those layers will always be out of reach. And maybe that's okay. Maybe the goal of science isn't to know everything. Maybe it's to know as much as we can, and to recognize with grace where the boundary lies. To map the edge of the knowable, and then stand there quietly looking out at the darkness beyond. Not with frustration, but with wonder. Because the darkness is part of the picture. The unknown is not a failure, it's a feature. So, we'll never see the Planck scale. We'll never build the experiment. We'll never take the photograph. But we can still think about it. We can still dream. We can still ask what it might be like, what rules might govern it, what secrets it might hold. And in asking even without answers, we touch something deep. A kind of intellectual humility. A recognition that the universe is bigger, stranger, more intricate than we can fully grasp. And that's not a defeat, it's an invitation to keep wondering, to keep imagining, to keep pushing even knowing we'll never arrive. The Planck scale is locked, but physicists haven't given up. They've turned to theory, to mathematics, to pure thought. And in that realm, where experiments are impossible, they've built cathedrals of ideas. Theories that try to describe what the Planck scale might be, how it might work, what it might reveal if we could ever see it. These theories, string theory, loop, quantum gravity, and others are our best guesses. And they're beautiful, even if unproven, even if unprovable. When experiments fail, when instruments reach their limits, when nature locks the door and hides the key, scientists turn to the one tool that has no boundaries: mathematics. Pure thought. The ability to imagine what cannot be seen, to describe what cannot be touched, to build cathedrals of logic in the space where observation ends. For decades, physicists have been constructing theories about the Planck scale, not with microscopes or colliders, but with equations. Elegant, intricate, beautiful equations. And two ideas have risen above the rest, capturing the imagination of thousands of researchers, inspiring tens of thousands of papers, and yet remaining to this day unproven. They are string theory and loop quantum gravity, two different visions of what reality might be at its smallest, two different attempts to heal the wound between gravity and quantum mechanics, and both in their own way whisper the same strange truth. Space and time might not be what we think they are. String theory began almost by accident. In the late 1960s, physicists were trying to understand the strong nuclear force, the glue that holds quarks together inside protons and neutrons. A young Italian physicist named Gabriele Veneziano discovered a mathematical formula that seemed to describe how particles interacted at high energies. The formula worked, but no one knew why. Then, in 1970, Leonard Susskind, Holger Nielsen, and Yoichiro Nambu independently realized something astonishing. The formula made sense if particles weren't points, if they were tiny one-dimensional strings vibrating like the strings on a violin. At first, the idea seemed absurd. Strings vibrating. How could that explain particles? But the math was compelling. Different vibrations, different frequencies corresponded to different particles. An electron was one vibration, a photon was another, a quark, a third. The universe in this view wasn't made of discrete fundamental points. It was made of music. Tiny loops and strands of energy oscillating in patterns too small to see each pattern, giving rise to the particles we observe. It was poetic, and it was deeply strange. But string theory had a problem. To work mathematically, the strings couldn't vibrate in just the 3 dimensions of space we experience. They needed more, initially 26 dimensions. Later, a refined version called superstring theory reduced that to 10 dimensions. 3 of space, 1 of time, and 6 more curled up so tightly at the Planck scale that we never noticed them. Imagine an ant walking on a tightrope. To the ant, the rope is a one-dimensional line. But zoom in, and you see the rope has thickness, a hidden second dimension, curled into a tiny circle. String theory suggests space is like that rope. We perceive 3 dimensions, but there are more wrapped up in geometries smaller than atoms, smaller than quarks, smaller even than the Planck length. Research shows that these extra dimensions aren't arbitrary. They have shapes, complex, intricate shapes called Calabi-Yau manifolds. The exact shape of these hidden dimensions determines which particles exist, which forces operate the constants of nature, everything. Change the shape, and you change the universe. The problem is, there are an enormous number of possible shapes. Some estimates suggest 10 to the 500 different configurations. That's more possibilities than there are atoms in the observable universe raised to an unimaginable power. Which one is ours? We don't know. And without a way to observe the Planck scale, we might never know. But string theory does something remarkable. It unifies gravity with the other forces. In ordinary quantum mechanics, gravity is the odd one out, refusing to fit into the framework that describes electromagnetism and the nuclear forces. But in string theory, gravity emerges naturally. One of the vibrational modes of the string corresponds to the graviton, the hypothetical particle that carries the gravitational force. It's not added by hand, it's built into the structure. And at the Planck scale, where strings vibrate, gravity and quantum mechanics are no longer enemies. They're 2 aspects of the same thing, the string. Some physicists describe string theory as a theory of everything. Not because it explains every phenomenon, but because it provides a single framework that in principle could describe all particles and forces. It's a beautiful vision, but it comes with a cost. String theory makes almost no testable predictions. The energies required to see the strings vibrate are Planck scale energies far beyond anything we can reach. The extra dimensions are hidden undetectable. The theory is mathematically consistent, but empirically it's silent. You can't prove it, but you also can't disprove it. It exists in a strange limbo, elegant but untouchable like a poem written in a language no one can fully translate. Then there's loop quantum gravity, a different approach, a different philosophy. Instead of asking what particles are made of, loop quantum gravity asks what space itself is made of. And the answer it gives is startling. Space is not continuous. It's not a smooth fabric. It's woven. At the Planck scale, space is composed of discrete loops, tiny knots of geometry, each about a Planck length across. These loops connect to form a network, a quantum weave. and space-time emerges from their interactions, the way a piece of cloth emerges from threads. Loop quantum gravity was developed in the 1980s and 1990s by physicists like Abhay Ashtekar, Carlo Rovelli, and Lee Smolin. They started from general relativity, Einstein's theory of curved space-time, and tried to make it quantum. They discovered that when you apply quantum mechanics to geometry, its self-space becomes granular. It has a smallest unit, not because there's something smaller filling it, but because smaller stops making sense. The Planck length is the pixel, and each pixel is a loop, a closed curve, a gravitational field, vibrating, connecting, forming a dynamic, ever-shifting web. In loop quantum gravity, there are no extra dimensions, no hidden spaces, just the 4 dimensions we know, but understood at a deeper level. Time doesn't flow smoothly. It ticks forward in discrete steps, each step a Planck time long. Cause and effect still operate, but they're woven into the fabric of the loops emerging from the quantum correlations between them. It's a vision of space-time as fundamentally discrete, fundamentally quantum, fundamentally relational. Space doesn't exist as an independent stage. It's created by the relationships between loops. Take away the loops and there's no space, no time, just abstract mathematics. One of the beautiful aspects of loop quantum gravity is how it handles the Big Bang. In general relativity, the Big Bang is a singularity, a point of infinite density where the equations break down. But in loop quantum gravity, there are no singularities. As you compress space-time, the loops resist. Quantum effects create a repulsive force, a kind of quantum bounce. The universe doesn't collapse to a point. It reaches a minimum size about the Planck scale and then rebounds, expanding again. This leads to the idea of a big bounce. The universe before ours might have been contracting, shrinking, until it hit the Planck scale, then bounced into the expansion we observe. Cycles of contraction and expansion stretching back infinitely. No beginning, no end. Just an eternal rhythm. It's speculative, of course, but it solves problems. It removes the singularity, the point where physics fails. It suggests a mechanism for the Big Bang that doesn't require something from nothing, and it makes predictions, at least in principle. If the big bounce happened, it might have left imprints in the cosmic microwave background, subtle patterns in the distribution of galaxies. Scientists have looked. So far, they haven't found anything conclusive, but the search continues. Now, here's where things get interesting. String theory and loop quantum gravity are often presented as rivals, competing theories, incompatible visions. And in some ways they are. String theory starts with particles and builds space from their interactions. Loop quantum gravity starts with space and builds particles from its geometry. One uses extra dimensions, the other doesn't. One is background dependent, assuming a stage on which strings vibrate. The other is background independent, constructing the stage itself from quantum processes. They seem fundamentally different, but some researchers believe they might be 2 perspectives on the same underlying reality. Like the story of the blind men and the elephant, each touching a different part and describing it differently, but all touching the same creature. There are hints, tantalizing mathematical connections, suggesting that string theory and loop quantum gravity might converge at the deepest levels, that they're describing the same physics in different languages. But proving that, or even understanding what it would mean, is beyond our current reach. One thing both theories agree on is this: the Planck scale is where the magic happens. It's where space becomes loops or strings, where dimensions curl or weave, where time loses its continuity and becomes something stranger. And both theories suggest that beneath the Planck scale, the questions we ask might not make sense. Not because we're ignorant, but because the framework we use to ask questions, space-time, distance, duration, might not apply. It's like trying to ask what color a sound is. The question assumes categories that don't fit. Let me give you an analogy. Imagine you're looking at a digital photograph. From a distance, it's smooth, continuous, a seamless image. But zoom in, and you start to see pixels. little squares of color. Zoom in further, and the pixels dominate. The image dissolves into a grid. Now, imagine trying to ask what's between the pixels. The question doesn't make sense. There's nothing between them. The pixels are the fundamental units. The image is made of them. Similarly, space might be made of loops or strings. And asking what's smaller than a loop or a string is like asking what's between pixels. The question assumes a continuity that isn't there. Here's a common misconception. People sometimes think string theory and loop quantum gravity are untestable and therefore unscientific. But that's not quite right. They're untestable directly at the Planck scale, but they make predictions about regimes we might reach. For instance, string theory predicts certain patterns in particle physics, certain symmetries, certain relationships between forces. Loop quantum gravity predicts signatures in the cosmic microwave background, possible corrections to black hole thermodynamics. These predictions are hard to test, but they're not impossible. And as our instruments improve, as our telescopes sharpen, we might find echoes of the Planck scale in the data, faint whispers, indirect traces, not proof, but hints. There's also a philosophical question worth asking. What is the purpose of these theories if we can never fully test them? Are they science or are they art? And the answer, I think, is both. They're attempts to extend our understanding as far as thought can reach, to map the boundary of the knowable. And even if we can't verify them empirically, they serve a purpose. They discipline our thinking. They reveal inconsistencies, paradoxes, places where our current understanding breaks down. They inspire new mathematics, new ideas, new questions. They keep the conversation going, even in the silence of the unobservable. Some scientists spend their entire careers working on these theories. Decades of calculations, conferences, debates, papers. And they may never know if they're right. They're building cathedrals they'll never see completed. Cathedrals made of symbols and logic standing in the realm of pure thought. It's an act of faith in a way, not religious faith, but intellectual faith. The belief that understanding, even incomplete, partial understanding, is worth pursuing for its own sake, that the journey matters even without a destination. And maybe that's the real lesson of string theory and loop quantum gravity. Not that they're right or wrong, but that they're possible. That human beings, finite creatures with finite minds, can conceive of structures so intricate, so far beyond everyday experience, and describe them with precision. We can imagine the universe at scales we'll never see in dimensions, we'll never visit, governed by laws, we'll never directly confirm. And in imagining, we touch something transcendent, not truth perhaps, but beauty. And beauty in physics has often been a guide, not infallible, but reliable. So, the search for unity continues. Physicists scribble equations, run simulations, attend conferences, argue over coffee. They're trying to heal the rift between gravity and quantum mechanics, trying to describe the Planck scale not with experiments, but with thought. And the theories they've built, string theory, loop, quantum gravity, and others, are testaments to human curiosity, to the refusal to stop at the boundary, to the desire, maybe futile but undeniably noble, to understand the universe down to its roots, even if those roots are hidden forever. And yet, even with these towering theories, even with all the brilliance and effort poured into them, we're left with uncertainty, with incompleteness. The Planck scale remains mysterious. The equations remain unverified. The unity remains elusive. But there's a kind of peace in that, a recognition that some mysteries are too deep, too fundamental to ever fully solve. And that's not failure, it's the nature of reality, complex, layered, infinite in its subtlety. And we, standing at the edge, can only marvel. So we've traveled through numbers, collisions, foams, black holes, origins, impossibilities, and theories. We've seen the Planck scale from every angle thought allows. But there's one more step, one final drift, a place where all these ideas settle into something quieter, something more reflective, a place where we ask not what the Planck scale is, but what it means. for us, for knowledge, for the long, quiet wonder of being human in an infinite cosmos. There's a particular kind of silence that comes at the end of a long journey, not empty silence, not the absence of sound, but the silence of arrival, of having walked as far as the path allows and standing there at the edge looking out at what lies beyond. We've traveled tonight through the smallest distances the universe permits, through numbers that dissolve meaning, through collisions that can never happen, through time that might not have begun, through black holes smaller than atoms and theories too beautiful to prove. And now, here at the end, there's only one question left. Not what is the Planck scale, but what does it mean? What does it teach us about ourselves, about knowledge, about the strange, humbling privilege of being conscious in a cosmos we can barely comprehend? Let's start with what we know for certain. The Planck scale exists, not as a physical object we can touch or observe, but as a mathematical consequence of the most fundamental constants in nature, the speed of light, the gravitational constant, Planck's constant. These three numbers, measured independently, combined in a simple way, produce the Planck length, the Planck time, the Planck mass, the Planck temperature. And those numbers define the boundary where our physics breaks down, where space-time becomes uncertain, where the smooth fabric we trust tears into quantum foam. It's not speculative. It's built into the structure of reality as firmly as the relationship between energy and mass, or between electricity and magnetism. But here's what's profound. The Planck scale isn't just a limit on measurement. It's a limit on meaning. Below the Planck length, the concept of distance might not apply. Below the Planck time, the concept of duration might dissolve. We're not just saying we can't see smaller. We're saying smaller might not exist in any coherent sense. It's like asking what's north of the North Pole. The question uses the right grammar, but it points to nothing. The Planck scale is the edge of the map. Not because we ran out of paper, but because the territory itself ends. And that's hard to accept. Human beings are explorers. We've climbed every mountain, crossed every ocean, sent machines to other planets. We've split atoms and decoded genomes. We've looked back in time to the edge of the observable universe. And at every step, we've assumed that there's always something deeper, something smaller, something more fundamental. The Planck scale says no. There's a bottom. Not a bottom made of things, but a bottom where thingness itself gives out. Where the questions we've been asking for centuries, what is it made of? How does it work? Where does it come from? They all hit a wall. Not a wall we can break through. A wall woven into logic itself. This has philosophical consequences. For most of human history, we've operated on the assumption that the universe is fully knowable, that mysteries are temporary, that given enough time, enough resources, enough cleverness, we'll figure it all out. But the Planck scale teaches humility. It says there are truths locked away not by our ignorance, but by the structure of reality. We can think about them. We can theorize, but we can't test. We can't verify. We're left with mathematics elegant and beautiful, but disconnected from the empirical method that made science so powerful. And that's unsettling, because it means some of the deepest questions about the universe might never have answers we can confirm. But maybe that's not a tragedy. Maybe it's a gift, because it reminds us that science isn't about certainty. It's about curiosity. It's about asking the best questions we can with the tools we have and being honest about the limits. The Planck scale is a kind of cosmic modesty clause, a reminder that we're finite beings in an infinite cosmos, and some layers of reality will always be beyond our grasp. Not because we're stupid, but because we're small. And there's a strange kind of peace in accepting that. Let me tell you about a conversation that happened in the 1980s. Richard Feynman, one of the greatest physicists of the 20th century, was asked about the theory of everything, the dream of a single equation that would explain all forces, all particles, the entire universe. And Feynman said something surprising. He said he hoped we'd never find it, not because he didn't want to understand, but because he loved the mystery. He loved the process of discovery more than the destination. He believed that the joy of physics wasn't in having all the answers, but in the endless playful pursuit of better questions. The Planck scale embodies that spirit. It's a question we can never fully answer. And that's okay. Think about what we've learned. We've learned that the universe has a smallest size, a shortest time, a highest temperature. We've learned that space and time, which feels so solid, so reliable, might be woven from something stranger. Loops of gravity, strings of energy, quantum foam bubbling faster than thought. We've learned that black holes aren't just cosmic vacuum cleaners, but windows into the deepest physics places where the rules change. We've learned that the Big Bang, that moment of ultimate origin, is wrapped in a silence we can't penetrate. The first 10 to the negative 43 seconds of existence might be forever unknowable, not because we lack data, but because the concepts we use time-space before, after they might not apply. And we've learned something else, that human beings, despite our limitations, can reach toward the unreachable. We can construct theories about dimensions we'll never see. We can calculate energies we'll never produce. We can imagine geometries that exist only in equations. And in doing so, we touch something profound, not mastery, but connection. A sense that we're part of something vast and intricate, something that doesn't care whether we understand it, but allows us to try. There's a quote from the physicist John Wheeler, the man who named black holes and imagined quantum foam. He once said, "We live on an island surrounded by a sea of ignorance. As our island of knowledge grows, so does the shore of our ignorance." The Planck scale is that shore. The more we learn about it, the more questions it raises. What is space-time made of? Why these constants and not others? Is the Planck scale the same in every universe or just ours? Could there be layers beneath it we can't even conceive? Every answer is a doorway to 10 new mysteries. And that's not frustrating, that's exhilarating, because it means the story never ends. So, what do we do with this knowledge? What do we do with the fact that the universe has a boundary we'll never cross? I think we do what humans have always done. We tell stories, we make art, we write equations and poems. We gather around fires, real or metaphorical, and share what we've learned. The Planck scale isn't just a scientific fact. It's a story about the limits of knowledge and the persistence of wonder. It's a reminder that some of the most important things in life love beauty, meaning they can't be measured, they can't be reduced to numbers, and neither can the deepest truths of the cosmos. They can only be felt, imagined, wondered about. Here's a question for you. Does it matter if we never fully understand the Planck scale? Does it matter if string theory is never proven? If loop quantum gravity remains forever theoretical? If the quantum foam stays hidden? I don't think so. Because the value isn't in the answer, it's in the asking. It's in the fact that we, a species that evolved to hunt and gather on the plains of Africa, have taught ourselves to think about the structure of space-time at scales 20 orders of magnitude smaller than a proton. We've built tools, mathematical and conceptual, that let us glimpse, however dimly, the edges of existence. And that's a triumph, not of knowledge, but of imagination. There's a kind of poetry in the Planck scale. It's the universe's way of saying, I have secrets and you'll never know them all. And our response is, that's okay. We'll get as close as we can. It's a dance, a conversation without words, between the cosmos, vast and indifferent, and us small but curious. And in that conversation, something beautiful happens. We realize we're not separate from the universe. We're part of it, made of the same atoms, governed by the same laws, subject to the same limits. The Planck scale doesn't divide us from reality. It connects us to it by showing us where our understanding meets the unknown. And maybe that's the real lesson. Not that there are limits, but that limits are okay. That not knowing is not a failure. That mystery is not an enemy to be conquered, but a companion to be respected. The Planck scale will remain hidden. The quantum foam will continue to churn unseen. The first moment of the Big Bang will stay wrapped in silence. And we'll keep reaching toward it, not expecting to arrive, but simply because reaching is what we do. Because wonder is not about answers, it's about attention. And the Planck scale in all its strangeness deserves our attention. So, Tonight we've drifted through the smallest places the universe allows. We've touched the numbers, felt the theories, imagined the foam. We've stood at the edge of time and peered into the void where space dissolves. And we've come back not with certainty, but with something better. With awe, with humility. With the quiet recognition that the cosmos is deeper than we are, stranger than we imagine, and more beautiful than we can say. Max Planck never intended to discover a new scale. He was just trying to solve a problem about light. But in solving it, he opened a door to the smallest, the hottest, the briefest, the most extreme. A door to questions we're still asking answers we'll never fully find. And standing at that door looking through, we see not just physics, but philosophy. Not just math, but meaning. The Planck scale is a mirror, and what it reflects back is not the universe, but us. Curious, ambitious, humble, human. Sleep well, dream gently. Let the Planck scale drift in the back of your mind, a quiet reminder that the universe is full of layers and we've only just begun to peel them. In the smallest places, in the briefest moments, in the spaces between knowing and not knowing, the cosmos whispers. And if you listen closely, very closely, you might hear it. Not words, just the soft hum of everything that is trembling at the edge of meaning. Good night. Thank you for journeying with me tonight through the quiet mysteries of the Planck scale. I hope these whispers of the cosmos brought you comfort, curiosity, and maybe a touch of wonder. If you'd like to explore more gentle science, more stories told softly in the dark, there are other journeys waiting, other questions, other edges. Until then, rest well and let the universe hold you. Another story will find you soon.